Okay, if we look at this one, this was very similar to what I did, and there was a typo on here. The KB is 9.6 times 10 to the negative 7th. That is the KB that was on the chart. I had made a typo on your copy. So the first thing to recognize was that I have a salt, hydrazinium bromide. A salt dissolves in water and it breaks apart into two ions, hydrazinium and a bromide ion. The bromide ion is the conjugate base of a strong acid, so it has no pH effect. The hydrazinium ion is the conjugate acid of a weak base, so it will act as a weak base, or as a weak acid. So we set up the equilibrium. Hydrazinium is in equilibrium with hydrazine plus the hydrogen ion. There's no bromide in this equilibrium, and there's no HBr in this. That's where I saw a couple of groups running amok when they started. Once we have this set up, it's same old, same old. We have 0.2 molar, 0 and 0. Minus x, 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 0.2 minus x, x and x. This is an acid equilibrium, so we need a Ka. Since we don't have a chart for Kas for conjugates, we have to use the Kb chart, find the Kb for hydrazine, and find Ka from Kw. And then we plug in our Ka, x times x divided by 0.2. We solve for x, which represents the hydrogen ion concentration, 4.6 times 10 to the negative 5th molar. So the pH is 4.34, which is acidic. And I see some of you got slightly different answers. But we're going to write that off to algebra right now and not worry about that. Okay, explain the salt thing. Most salts, actually, all of the salts we're going to deal with in Chapter 16 in this section are soluble. Okay? So, when we put them in water and make them aqueous, they make a cation and an anion. This cation can be the conjugate acid of a weak base, or it can be a metal. Those are the two kinds of cations we'll deal with in this chapter. If it's a metal, like sodium, potassium, lithium, it has no pH effect and we ignore it. If it's the conjugate acid of a weak base, we set up an acid equilibrium and we find the Ka by taking Kw and dividing by Kb. So maybe the cation has a pH effect, maybe it doesn't. The one we just looked at was an example of a conjugate acid of a weak base. So it had pH effect. The anion can be one of two things for this chapter. It can be the conjugate base of a strong acid. And if that's the case, it has no pH effect, because strong acids break apart completely, and their anions have no interest in hooking up with a proton again. So they just sit there. That's things like the chloride ion or the bromide ion or the nitrate ion. They'll just sit there and do nothing. Or the anion can be the conjugate base of a weak acid. And that's what we're going to look at in the next problem. So if the anion is the conjugate base of a weak acid, it will set up a basic equilibrium. The anion will react with water and make a basic equilibrium. And we need to find the Kb for that basic equilibrium, and we do that by dividing Kw by Ka. So the next example is one of those, a conjugate base of a weak acid. Okay, does that answer your question? So we've talked about our generic weak acid, HA, and now we think about A-. This is something like acetate. If I put sodium acetate in water, it's a salt, and the acetate ion is the conjugate base of the weak acid, acetic acid. Okay, so these A- anions react with water to make the weak acid plus a hydroxide. This is the conjugate acid of a weak base. In this case, the conjugate acid of the weak base is a neutral acid, and our base was a negatively charged anion instead of a neutral molecular compound like an amine. Okay, let's look at an example now. What's the pH of 0.1 molar sodium hypochlorite solution? Well, sodium hypochlorite has a sodium ion. That's an alkali metal, so it is very soluble. The salt breaks apart completely and makes a sodium ion, which has no pH effect because it's an alkali metal, and a hypochlorite ion, which is the conjugate base of a weak acid, so it will act like a base. Since it acts like a base, I need the Kb for the hypochlorite ion. So Kb is equal to Kw for hypochlorous acid, is equal to Kw divided by the Ka for hypochlorous acid. So 1 times 10 to the negative 14th divided by Ka, which I go look up on the chart, hypochlorous acid, 3.0 times 10 to the negative 8th. So my Kb is 3.3 times 10 to the negative 7th. It's a nice small number, so I can simplify my math and assume x is going to be small in this example. So now I had 0.1 molar salt, and I get 1 hypochlorite from 1 sodium hypochlorite, so my hypochlorite concentration is 0.1 molar. When I'm setting up my ice chart for a base, I ignore water. So I have 0.1 molar. Now, once I have my chart set up, same old, 0, 0. Change is minus x, x, and x. At equilibrium, 0.1 minus x, x, and x. Because my Kb is 10 to the negative 7th, we can assume x is small, and this is just about 0.1 molar. So now I set it up. My Kb is equal to the hypochlorous acid concentration times the hydroxide concentration divided by the hypochlorite ion concentration. 3.3 times 10 to the negative 7th is equal to x times x divided by 0.1. Now we do the same math we did over and over in the previous sections of the chapter. So multiplying across, I get 3.3 times 10 to the negative 8th is equal to x squared. X represents hydroxide here because I have a base, so that is 1.8 times 10 to the negative 4th molar. So the pOH is 3.74. Now I need to find the pH from the pOH and pKw. pKw is 14 minus 3.74, so the pH is 10.26. And now when we look at that, we say, yeah, that seems reasonable because this is a base, so I would expect it to have a basic pH.